going to prove this theorem that we mentioned last time. Let T from V to V be a linear operator a bit quiet please. So suppose we have such linear operator, then the following are equivalent. So use TFAU for the last one. So the first one is T is diagonalizing. The second is that T admits an eigenbasis of V. What is the third one? V equal to this direct sum, right? So if lambda 1 or lambda m are distinct, lambda r, right? Yes. Are distinct eigenvalues of T, then V is equal to E lambda 1 direct sum lambda r. Okay. Fourth was what? For each of the eigenvalue, right. So or could you please get some more yellow chalks? Thank you. For each eigenvalue of T, the arithmetic multiplicity and the geometric multiplicity of each eigenvalue lambda c, each eigenvalue lambda of T, the arithmetic multiplicity and geometric multiplicity of lambda are the same. And we can also note down here a fifth. I'm writing it here because we want to use both of the other codes for the proof. Fifth is that the sum of the geometric multiplicities, that is the sum of these dimensions, what it should be? M, right? Exactly. Yeah. All right. Yeah. But nevertheless, here you are like proving that V is equal to this, whereas this is equivalent to just the sum. That is, if the sum of the geometric multiplicities of all the eigenvalues of T or of the eigenvalues of T, because geometric multiplicity just means that you are summing up the geometric multiplicity of the distinct eigenvalues, right? Of values of T is dimension V. Indeed, it just follows from here, but also this follows from here as well. It's rather trivial. Let's see. So proof. The first thing is that T is diagonalizable. But what does it mean? There exists some basis. Well, perhaps you can tell me what it means for this to be diagonalizable. Alvin? What it means for a linear operator to be diagonalizable?
That means there exists a matrix
Yes. And in terms of basis and matrix representation of T? In terms of basis and matrix representation of T? So suppose A is a matrix representation of T with respect to some basis. What can you say about that? What it means in terms of other, that is also a matrix representation of T, right? With respect to a different basis. So this just means that there exists some basis with respect to which the matrix representation of T is diagonal. Alright? So Ananya, Ashmit, Ashay, and Devan, you are in today's group, right? Group S. So please take a note. So one means just that there exists a basis B of V such that the matrix representation of T with respect to B is diagonal. Okay. So let's write it down. How do we relate these two things? The matrix representation T, the matrix representation of T and V. We define this in this manner. T of V is equal to V times now a diagonal matrix. Okay? So write it down as D. That D is diagonal. Diagonal matrix representing T. Okay? So suppose the elements of B are V1, V2 to Vn. Okay? Vn. Then Tv is just Tv1 Tvn, right? And what is that? That is equal to V1 Vn times this diagonal matrix, right? Lambda 1, lambda 2, lambda n. Alright? So let's check what is the image of Tv1. So this is, or say any Tvi. Okay? So this is if and only if T of Vi is equal to what it should be? Lambda I, right? Because it should be the ith column. This times the ith column. So the ith column, the linear combination given by the ith column of these matrices. And what is in the ith column? Lambda in the ith place and 0 everywhere else. Okay? So this is Tvi that is given by lambda Vi. Lambda Vi is the entire linear lambda I here, sorry. This is the entire linear combination that is given by the ith column. Okay? In other words, each of these things in the basis should be an eigenvector of T. Right? Because T of Vi is lambda Vi for some scalar lambda. Okay? In other words, since each of the elements of the basis B is an eigenvector of T, we call such a basis an eigenbasis. So that is eigenbasis. A basis of B such that each element of that basis is an eigenvector of a linear vector. In particular, here T is given, so eigenvector of T. If such a thing exists, if such a basis exists for which this happens, that is Tb is equal to Bd, we say that T admits an eigenbasis of B. So this is obvious from the definition of diagonalization. You see? And on the other hand, if there exists an eigenbasis, then try to represent, try to find the matrix of T with respect to that basis. So how do you do that? T of B would be equal to B times some matrix. Okay? Which matrix it should be? That will be exactly this one. This will be the eigenvalues on the diagonal. Note that these eigenvalues may not be all distinct. What we require here is that this V1 to Vn are linearly independent. In fact, all this lambda 1 to lambda n can be the same thing. Okay? For example, take the n cross n identity matrix. All are 1. And what is the role of this V1 to Vn there? Actually, you can take any linearly independent vectors. In particular, you can take also the standard basis. Okay? So, is it clear that this and this are equivalent? So, this implies 2. I know that whatever we have done here to get from 1 to 2, we can trace it back and get T. Okay, get 1. That T is diagonalized. So 1 implies T is kind of obvious. Then let's come to the third.
Is how you show that V1, Vn, Vn are
eigenvectors.
Eigenvectors. So how can you tell that they are independent?
Because you are starting with the basis P. And on the other hand, if you are starting from 2, you are already saying that T is an eigenbasis. So you are given a basis of eigenvectors. So 2 implies 1 is rather trivial, or we just saw the proof of that as well. It is just the opposite argument. Now 3. Well, what do we know about 3? That this one, the lambda 1 direct sum, dot 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 direct sum,
Sir,
lambda, yes?
so what does admit mean?
Just a minute. V1 to V2 to Vn. No, it's fine. Because n we are assuming to be the dimension of V. Okay. Just 1 minute, fine. Yeah, so this one, such a thing, consider an eigenbasis. So what are the two things involved here? One is a vector space, another is T, and the linear operator. Okay. But you cannot say that it's an eigenbasis of T, because T is an operator. How can you speak about a basis of an operator? So you have to talk about a basis of the vector space. But nevertheless, you have to associate that basis with T as well somehow. Okay. So that's what we mean by this one. That is, T admits an eigenbasis of V. That means that there are eigenvectors of T. The coordinate of there exists a set of linearly independent eigenvectors of T. The coordinate of each set is exactly equal to its dimension, the dimension of T. If that happens, then T is diagonalized.
Sir?
Yes.
Sir, in that case, you first of all you wrote that T of B equals to B into D.
T of
B equals to B into D.
T of B equal to B into D. Right. Where we are assuming that is diagonal.
D is diagonal.
Right.
And then you use the fact that B is a basis.
For B, we are just using if we are going from here to here, we are just using the fact that B is a basis. We are showing that it's an eigenbasis. Okay. That each element of the basis should be an eigenvector.
Then you written that T of B equals to T of V1 to T of Vn.
Yes, it's a definition of T of B, right?
Then you made an equality with V1 to Vn.
That is this one B. Okay, and then you have a diagonal matrix.
But how do you know that the diagonal matrix have the entries of the
You do not know, but you know that there are some diagonal entries, and those diagonal entries have all of these diagonal entries must be the eigenvalues. We just saw it, right? If you complete if you look at the details, if you expand B like this, if you multiply this and this, then at the ith position here you are getting T of Vi, here you are getting lambda I Vi. Okay? So each of the elements of the basis B have to be, each of this has to be an eigenvector, and the corresponding eigenvalue would be the corresponding scalar on the diagonal of this matrix. And vice versa. If it admits an eigenbasis, that means you are already having a basis, okay, with respect to which the matrix of T is diagonal, made of the eigenvalues of T. Alright? Yeah.
Could you again about admitting a certain things by an operator means?
Well, forget about admitting. We have to associate this eigenbasis both with V and T. And you cannot say that it's an eigenbasis of T. T is an operator. How can you define a basis of an operator? Okay. So this sentence just means that there exists a basis of V, each of whose elements are eigenvectors of T. So this sentence actually means that's it.
This means there is an eigenbasis.
So we could write induces and eigenbasis.
No, that's not the standard terminology.
It's language.
Yeah. So E lambda 1 plus E lambda r, we know that this is a subset of V, subspace of V. Now we say that if it is diagonalizable, then there exists an equality. So let's begin with this one again. If wait a minute, if it is diagonalizable, we have TP equal to PD, right? And we saw that each of these each of these basis vectors should be an eigenvector of T. Some of them could correspond to the same eigenvalue. In fact, all of them could correspond to the same eigenvalue. We don't care. So what we see here is that if we take the eigenspaces, so if we sum up, say, suppose we are just considering the eigenvectors which are the same. So suppose lambda 1 equal to lambda 2 equal to lambda 3, and the rest are different. Okay? Denote this, club them together, call them lambda. Okay? And then you see that the elements of this basis B, which are eigenvectors corresponding to this lambda. I mean, if you consider that space of eigenvectors, which are that space spanned by these three eigenvectors corresponding to lambda 1, lambda 2, and lambda 3, that will have dimension 3, right? And we know something from here, that is, so dimension of E lambda 1 plus dimension of E lambda r, this is less than or equal to n. So for each of these eigenbases, you can find, if you take the basis for each of this one, if you could just put them together one after another, that will form a basis of this space. And since the dimension of this is less than or equal to n, so unless you take the full basis for each of these ones, you cannot possibly get n.
So we are saying direct sum, right? Then by less than equal to 0, it should be.
It's a subspace. Okay, so this could be a proper subspace in general. Yeah, Akshay.
Don't we first need to prove that these eigenspaces are independent?
We have proved this already. So this was in one of the previous classes, don't you recall? Just take any linear combination of vectors belonging here, apply T, and then you can remove one of those vectors. So assume that you have a minimal set of dependent subspaces of this, starting with E lambda 1, say E lambda 2, E lambda m. Then you have V1, V2 to Vm, apply T on them, and then you can actually remove Vm, the last one, say, or remove any of them. Well, since we are saying that m is minimum, so m is a minimum such number, you can remove Vm. You are getting a relation between the first m minus 1 things. That's a contradiction. And this has to stop somewhere because each of these spaces are non-zero by definition. They are eigenspaces. So yeah, now look at this one. That is, if suppose this, lambda 1, lambda 2, and lambda 3 are equal. Okay? That means what? Dimension of E lambda corresponds to this one, lambda 1, lambda 2, lambda 3. We are in this setting again, not there, but here. We are starting with a linear operator which is diagonalizable. We write it down like this, and this lambda 1 to lambda n are just the diagonal entries. Okay? Now, from here we know that all these diagonal entries should be eigenvalues. Okay? May not be distinct, but at least eigenvalues. Okay? And now what we are doing, we are clubbing the same eigenvalues together. So what we get then, the span of the corresponding eigenvectors would give you the corresponding the basis for the corresponding eigenbasis. That's what we are trying to prove. At first, we are assuming that suppose we club this together, say the first three things together, or something lambda. Say the first three things are the same, and this is the corresponding eigenvalue lambda. Okay? Then dimension of E lambda. What can you say about dimension of E lambda and 3? Is it equal to 3, less than equal to 3? I mean, whatever we have done here, what it means. We are not using this one at all. We are just using this one. So is it equal to 3? Is it greater than 3? Is it less than 3? What is it?
It's 3.
It is
3. Equal
equal to 3. We do not get equality here because we do not know that whether it's reached. At least we know that there are 3 independent eigenvectors corresponding to the eigenvalue lambda. So that could be a full basis of E lambda. That could be a part of the basis of E lambda. Okay? We could extend it. Okay? So we know that this is greater than or equal to 3. At least there are 3 elements which are linearly independent. Suppose the first 3 are equal, lambda. Then we were trying to figure out what is the relation between the dimension of E lambda and this 3. Which, I mean, the 3 is coming from the first 3 the first 3 elements on the diagonal are the same. So this dimension of E lambda, this should be larger than or equal to 3 because we are getting at least 3 linearly independent eigenvectors. Alright. So, and that happens for each of the eigenvalues that we are getting on the diagonal. So we are clubbing the same eigenvalues together now. And we are now getting the span of the corresponding eigenvectors. And then all we can say is that the corresponding eigenvectors, the span of this could be E lambda or could be a subspace of that. Okay. So the dimension of E lambda is larger than or equal to the number of the times the eigenvalues appear on the diagonal. Alright? Is it fine? So in particular, you are getting, so suppose for each of, now lambda 1 to lambda are the distinct eigenvalues of this one, right? Of t. Okay? So suppose the number of times this lambda 1 to lambda r appear on the diagonal, this numbering is something different from this numbering. We are using the same thing. That's right. So we have use here all primes. Okay. Not to confuse them with the distinct ones. These are some values on the diagonal which we know that they are eigenvalues, but not necessarily distinct. All right. So now what we are getting, say define n lambda I to be the number of times lambda appeared on the diagonal. I have to wipe out this part, the first part. I hope it's fine. We are not wiping more than this one, this part. Just the first two lines. So we are defining n lambda I to be the number of times lambda I appear on the diagonal. On the diagonal of this matrix D. Okay. So what we can say from here that sum over n lambda I, note that this lambda I could also be 0. There could be, I mean, apparently at the beginning we know that these should be the eigenvalues, but we do not know whether all the eigenvalues appear there. Okay. We haven't, unless you compare the dimensions, you do not know whether you have all the eigenvalues there. You at least you know that all of these are eigenvalues and these elements of D are the corresponding eigenvectors. Any difficulty here?
So is it trivial that the direct sum of the eigenspaces is it subspace of D?
We proved this, didn't we? At first, each of these eigenspaces are subspaces of D. Right? They are collection of eigenvectors.
Sum is also a subspace of D and they are independent.
They are independent. So it follows that the direct sum is a subspace. Now, what can you? Yeah.
So to share that, we can say that it will be there will be n because I mean there are v1 to vn, right? So
V1 to Vn.
so for them to be multiplied, there needs to be n values on the diagonal.
Then there needs to be n values on the diagonal, but these are some diagonal values. I mean some elements on diagonal, and we do not know whether all these distinct eigenvalues appear there. A priori, we do not know that. So in particular, this n lambda I, we allow it to take value. I mean, this could also be 0. So this is somewhere in n Vn. 0. Because there could be some of the eigenvalues which are, I mean, a priori we do not know whether all the eigenvalues appear here or not. We know that whatever appears here are eigenvalues, and whatever appears in B therefore are eigenvectors. But we do not know whether B covers all the eigenvectors. I mean, B has eigenvectors corresponding to all the eigenvalues. Whether all the eigenvalues are appearing here. So in lambda I a priori could take also values in this set, I mean, could be 0. But we know something, that is this n lambda I, the sum of this is equal to n, the dimension. N, that is, well, let us write dimension of the, which we take to be n because this is an n cross n matrix. Now, what is the relation between n lambda I and these dimensions? Dimension of E lambda I set. So n lambda I, yeah, right. We just saw it right here with taking the first three things the same. That is, this one is larger than or equal to 3. You can have at most as many linearly independent things as the dimension of these ones. I mean, for corresponding to an eigenvector value lambda, you can have at most dimension of E lambda I linearly independent eigenvectors corresponding to the eigenvalue lambda I. So that means this is less than equal to this. Okay. Thank you, everyone. Oh, because this is the number of times this is appearing on this one, and this is an n cross n matrix. Okay. Now sum it up from on the left and on the right. So after this, what we do? One of you to get some yellow chalks? Is there? Okay, thank you. Summation in lambda. Well, we are summing it on both sides. Say here. Just we write the sum here, and then we take also the sum here over the different i's. Lambda i's. Note that this lambda is a distinct eigenvalues. Now, corresponding to those ones. These ones we are now denoting just by grams. Alright. So what do you know about this and this? Summation n lambda I first. This is equal to n. And if there is equality, like this one, well, at first, we don't know that whether there exists equality, right? We only know that this is less than or equal to n. This is true for any vector space. Okay? So what do you get here? That this is less than or equal to n, right? Alright? So from here, what do you get? That this and this are the same thing on the left hand side and the right hand side. So this should be an equality. Everything here would be an equality then, because this one is n, on the right hand side is also n. So from here it follows. I hope now it's fine to wipe this part out. Well, a and tm are still left, but this will be like, I mean, rather simple after this. So we. Alright. So this one then implies that n is equal to summation n lambda I equal to summation I e lambda I equal to n. And since each of these is also, since n lambda I is less than equal to dimension of e lambda I for all I, what can you conclude from here then? Their sums are equal and each of these terms are less than equal to this. These are non-negative things. And these are less than equal to e lambda I. So what can you conclude now from there?
That should be dimension of
Ah, right, yeah. Thank you. Yes. Yeah. E lambda I. Dimension of E lambda I. That's equal to n. Okay. you conclude from here then? No, at first, what can you conclude about each of these n lambda is? We know that this is less than equal to e lambda, right? For each I, right? Because, yeah. So that implies that n lambda I is equal to dimension e lambda I for all I. Right? By the way, what was this? This was, let me write this once more. What we just wiped out, V1, Vm. This was right? So what are you getting? That is, if n, what was n lambda I? N lambda I was the number of times lambda I is appearing on the diagonal. So what it means? Lambda I appears on the diagonal just as many times as its geometry complexity. I mean, if it is diagonal, it is appearing on this. Yes, we are going to that. But at the moment, whatever this implies is that this equality just implies that the number of times this lambda I is appearing on the diagonal is exactly equal to its geometry complexity. Okay? All right, and that means this V is just the direct sum of, well, V is just a union of all the, you are taking different bases for the different eigenspaces, and you are just taking the union of them, and you are getting V. Any doubts on what we are doing here? Note that the number of times lambda I appears on the diagonal is equal to the number of times the corresponding eigenvectors appear in this basis, right? So how many times the corresponding eigenvectors are appearing in the basis B? Exactly as many times as the geometric multiplicity of lambda I, right? So that implies, in particular, now we can wipe this out.
Sir?
Yes?
Sir, why do you say n lambda I belongs to n union 0? I mean, why you are not sure that all the lambdas might not be there in that number?
This is not a priori given to you. All you know is that it's diagonalizable. And from the definition of diagonalizability, we know that each of the vectors in the basis should be an eigenvector. But we do not know whether all the eigenvalues are appearing there. You have some basis made of eigenvectors.
Can you give an example?
We cannot give an example. We just saw that this is not possible. If it is diagonalizable, we are proving that if this is diagonalizable, then V is equal to this. So, a priori we are assuming that this in lambda could take values which are equal to 0. And we are showing that that is not possible.
I mean, we are apparently then prove that n lambda I cannot be there.
N lambda I cannot be 0. Not only that, n lambda I should be equal to the dimension of E lambda. It cannot take values which are smaller than the dimension. Okay. So, yeah. This implies, in particular, that the sum E lambda 1 direct sum E lambda n, lambda r, sorry. If you take the sum, then this is equal to n, right? The dimension of yeah, right, of course. Sorry. If we take the sum of the dimensions, then it is equal to n. But if you are just taking the direct sum of subspaces, it is equal to n. Or this is the same. And also mentioned that the dimension E lambda r is equal to v. So we get both these implications, that is 3 and 5 both are done. Yes.
So what is R?
R is a number of distinct eigenvalues. You see, lambda 1 to lambda r are distinct eigenvalues of T. Which one? Thank you. It's equal to dimension of T. Thank you, Rafael. So this implies that 1 implies both 3 and 5. Right? Let's check whether they apply it back. So suppose V is this one. Okay? V is the sum of these eigenspaces. Take the corresponding eigenvectors, eigenbases of each of the subspaces. Take the union. That gives you a basis of V. Right? So what I want to say is that I just write this definition. So now we are checking whether 3 and 5, 3 or 5 both are implying at first. So while I am writing it down, even Akshmit was mentioning that these two are equivalent. Indeed, 3 and 5, these two are equivalent. Is this clear to you? If not, please let me know. Because what it is, the geometric multiplicities are dimensions of this. And you know that this is a subspace of V. So if the dimension of this matches with this, sum of the geometric multiplicity is just the sum of the dimension of this one, the right hand side. If that matches this one, since this is a subspace of this should be equal. Right? On the other hand, if this is equal to this, then take the dimensions on both sides and you get 5. Right? So 3 and 5 are equivalent, that is obvious. On one side we are talking about the direct sum of subspaces, and here we are just talking about sum of numbers, sum of positive numbers. Now, let's check whether 3 implies 1. So what does 3 imply? That V is equal to E lambda 1 direct sum, direct sum, E lambda R. Right? And then that means if you take, say, B1 or Bi to be a basis of E lambda I, and then define B to be just the basis where you augment all of this, B1, B2, Br, then the claim is that this is, well, at first, this is an eigenbasis of V. Pardon? Are you got it? Yeah. So what we are doing is that Bi, we are taking Bi to be a basis of E lambda I. Okay. Excuse me. You, in the middle. Oh, what's your name? Yeah? So can you tell me how we are getting from 3 to 1? We just discussed the proof. That is from 3, how do we go to 1? You are looking at your phone, not at the board. Please pay attention. Otherwise be out of the class. Whichever you prefer. We are repeating the logic. So V is this one. V, we are taking it to be E lambda 1 direct sum E lambda R. Okay. What are these? The eigenspaces corresponding to this eigenvalues lambda 1 to lambda R. These are the distinct eigenvalues. So then we are taking Bi to be a basis of this E lambda I's. Now this one, B1, B2 to Br, we are just augmenting the basis. I know that this, if you take the augmented thing, call it a basis, call it an element, sorry, a set B, this is going to be a set of linearly independent vectors. Because these are independent, right? We proved this earlier in the previous class also. Today we discussed how we prove this. So this is a set of linearly independent vectors of, and the continuity of this set is exactly equal to the dimension of V, because V is equal to this. And therefore, we are getting a basis made up of eigenvectors of T. What do you call such a basis? Louder? Yes. Eigenbasis of T. Eigenbasis of V admitted by T. Because each of these are, the elements of the basis are eigenvectors of T. And now, suppose we try to figure out what is the matrix relation of T with respect to this basis V. So can you please tell me what is TP? how it should be. Suppose we are considering V1. The first thing is V1, right? And what are the elements in V1? The eigenvectors correspond to lambda 1. Okay? So if you write those elements here, say, so how do we figure out the matrix representation of V at first? We just want to write V times some matrix A. And the columns of A are giving the linear combinations of the elements of V, which are giving you the, so you are applying T on V1 set, and the corresponding vectors would be the first few elements of this one on the right hand side. And these are the corresponding linear combinations of the elements. So anybody can tell me what A should look like? Yes. It will have the eigenvalues corresponding, say lambda 1 at first. The first dimension lambda 1 things would be just the corresponding eigenvalues lambda 1. Then so A should be looking like lambda 1 dot lambda 1, then lambda 2 lambda 2, and so on. Okay. The eigenvalues will be repeated as many times as the dimensions of this. Okay. So in particular, this would mean that T is diagonalizable. T has a matrix representation which is diagonal. So 3 implies 1 indeed. So is the logic clear to you? Yes, Arjun. Which one?
Lambda 1 is being repeated the number of times the dimension of lambda 1, E lambda 1.
Lambda 1 was repeated in a matrix, yes, right?
So from here can you conclude that the AM and GM of each lambda are equal?
Well, we are not going to that immediately because we are now here. We will, yes, of course. Indeed, what you are saying is that from 3, 4 will follow immediately. But at the moment we are seeing whether 3 is implying 1. So let's concentrate on that. So all we are saying here is that this A should be diagonal. And on the diagonal, the eigenvalues will be repeated as many times as the number of elements in each of these VIs.
So could you repeat why it should be diagonal?
Yeah, sure. So what are V1, V2 to be here? What are these? Basis of what? Right, the eigenspace. Okay. So in particular, all the elements in this are eigenvectors of T. What do you call such a thing? Right. What do we prove here? T admits an eigenbasis if and only it is diagonalizable. Right? So if all these things are eigenvectors, then here you have the set of eigenvectors, here you have the set of eigenvectors, and this A would be just a set of corresponding eigenvalues on the diagonal. Let's recall, do you recall still how we went from here to here?
Basically, we are going from 3 to 2 and then 2 to 1.
Yeah, actually we proved that 1 and 2 are equivalent. Then we are proving that 1 and 3 and 5 are equivalent. So each time we are coming back to this one. So yeah, this one, that's why the matrix should be is of this form. Is it clear, or should we go over it once more? Yeah. Yeah.
Sure. Didn't we prove the fourth one
Yes.
in that part n lambda I is equals to dimension of E lambda I?
No, yeah.
That is the
basically
proof, right?
that is. Yeah, perfect. So at first, 3, and we just saw that this implies 1. And here we have seen that 1 implies both 3 and 5. So these two equivalents are done. And now we come to this one, that for each of the eigenvalues, arithmetic multiplicity and geometric multiplicities should match. Alright. So from this matrix representation, okay, at first, let's recall what was the definition of algebraic multiplicity.
Number of times lambda appears in the characteristic polynomial.
Right. As a root of the characteristic polynomial.
Yes.
And then we know something that if you take a conjugate of a matrix representing T, suppose A is representing T. Forget about that A is of this particular form. But suppose you have this equation TB equal to BA for some basis B. Then if you change the basis, does the characteristic polynomial change?
No.
It doesn't, because this one changes just by conjugation. And the characteristic polynomial is defined as a determinant of Di minus A. So that doesn't change. In particular, the roots of the polynomial doesn't change. What are the roots of those polynomial? That polynomial? Lambda 1 to lambda n. Right? And here we saw that if such a thing exists, then the corresponding shape of A would be lambda 1 dot dot dot. Okay, I need a bigger board for this to write it down. But this ni lambda I will also require. Can I wipe this part of the entire board? What? Oh, yeah, indeed, because it's the last part. We can certainly wipe the theorem. Alright, so PB equal to BA, where this A is of this form lambda 1 dot 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 lambda 1 and lambda 2 dot 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 lambda 2. Still a bigger space is needed, so lambda 2 lambda 2. So it writes it lambda r dot 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 lambda r. Ah, that's better. Yeah. Yeah, sure. So this is equal to lambda 1 times
NR.
well, dimension of this, or nr, n lambda. Lambda 2 times I n lambda 1, lambda 2, lambda r times I n lambda r. Alright? This n lambda is because what were the number of times it is getting repeated on the diagonal. And we know that this n lambda is each are equal to this to the dimension of this. Okay? So for our matrix to be diagonalizable, we require this n lambda is the number of times it is repeated on the diagonal should be equal to this dimension of E of lambda. And if that is true, at first, what is the algebraic multiplicity of lambda 1 for this matrix?
In lambda.
N lambda 1. What is the algebraic multiplicity of lambda 2 for this matrix? Lambda 2, n lambda 2, and so on. Okay? So this one implies that algebraic multiplicity of lambda I is equal to n lambda I. Okay? And in between, while we are considering, while we are trying to prove that this is equal to V, we already shown that this n lambda I should be equal to these dimensions. Right? And this was an if and only condition. We also went from here to the diagonalization. So what we are proving here is that 4 and 5 are equivalent. Not 4, sorry, 3 and 4 are equivalent. 3 and 4 are equivalent. And since 3 is equivalent to 1, so indeed 4 and 1 are also equivalent.
But sir, that is trivial in that state, right? In lambda equal to d dimension
Exactly.
of lambda, and you take the sum.
Sure, it's just a different statement of the same.
Exactly.
So can we say that n lambda equals to the dimension of E lambda, and that follows that A equals to J?
Yes, of course, yes. So immediately from there, yeah, I think both Akshmit and Ridhiman, they concluded at that time when we were writing down in lambda, and you said that we'll discuss later when we talk about 4. So yeah, basically that was the proof of this. But I just didn't want to confuse you because we were talking about some other point. And now, indeed, it was that this n lambda I should be equal to the dimension, and that is the proof of algebraic multiplicity and geometric multiplicity for each of the roots should match. Note that this n lambda 1 and n lambda 2, this could be different. All we know is that for each of these ones, the dimension of the corresponding eigenvalue, the eigenspace, the dimension of the corresponding eigenspace should be equal to this n lambda I, which is equal to the algebraic multiplicity of the root. So that's it, and I think that actually finishes of the class.